Howdy guys, good afternoon. Welcome back. Sorry about that. Just a little bit scatterbrained today, but today I want to talk to you guys a bit about the chain rule. Honestly, I don't have a whole lot for you guys today. You guys are ahead of my other Calc 1 classes, and I want to kind of try to keep them paced the same. And since Thomas and Haley and Tahara were so efficient in their lectures over the last few days, I really don't have anything for you today. Nothing special that we need to get through. But I can go ahead and introduce the chain rule. I can solve a few other problems for you guys if you like. So let me go ahead and turn on the share, and we'll talk a little bit about upcoming exams, because we do have some of that discussion to do. So today will be short. I know the syllabus has us doing the chain rule this week, but we don't really have time to give a proper treatment of the chain rule, and I haven't put any chain rule problems in your homework because product and quotient rule are really enough for this week. You need to get comfy with the power, product, and quotient rules before I can start dropping chain rule stuff on you. So, today we'll do a little more practice with the power, product, and quotient rules. And then we'll talk a bit about exam 1. And maybe we'll introduce the chain rule a little bit. This is all I have planned. So are there any particular homework problems that you guys would like to look at? Any problems from the WebAssign set this week that have been giving you a tricky time, or that you would like to see? Not so much. I have a few in mind. Some velocity stuff, sure. I don't think I've given you a whole lot of velocity stuff this week. Not a bunch of physics in here. There are some from last week, but let's see what we got. So here's our definition of E. Some of these are sneaky, fun things. Search. So here's a velocity problem. Looks like this is the only one in here that mentions velocity. So I'd be happy to work this one with you guys. We can try to contextualize it as much as possible. So they say the equation of motion for a particle is s equals t cubed minus 27t, where s is in meters and t is in seconds. So this is an example. It's coming from homework 4. It's number 22. And they say that a particle moving along a straight path has position s of t equals t cubed minus 27t, where t is non-negative, greater than or equal to 0. And they say find the velocity and acceleration. Functions. So we can talk a little bit about what velocity and acceleration are, and kind of intuitively try to understand them. I think this is worth doing. Velocity is the rate of change of your position. right? It's how fast is your position changing over time. So if this is your position, then your velocity is the derivative of that, taken with respect to time. It's the instantaneous rate of change. So kind of how fast are you going at any given moment? Or what does your speedometer read in the car, right? That's a good way to think of velocity. Acceleration is how fast your velocity is changing. And one way you can think of acceleration is in the car, that force that you feel pushing you back into your seat when you like press on the gas and you feel yourself pushed back into your seat. That's acceleration, right? It turns out Newton's second law, F equals ma, is that force you feel is proportional to the acceleration, which is the rate of change of your velocity. So if your velocity is 0, then your position isn't changing, right? If your velocity is 0, then your position is constant. If your acceleration is 0, then your velocity is constant, which means you're going at a steady speed. So no acceleration means constant velocity or steady speed, no change in speed. So intuitively, those are what these things are. There's also higher derivatives of position called jerk, jounce, snack, crackle, and pop. Jerk is what it sounds like. When you go over a speed bump, you feel this like really intense jerky motion. It's the third derivative of your position taken with respect to time. And then the term jounce is kind of silly. That's your fourth time derivative of position. And then snap, crackle, and pop are really just very silly. But those are the fifth, sixth, and seventh derivatives taken with respect to time. So the ones that we really care about for the purposes of physics, your velocity is the derivative of your position taken with respect to time. Yeah, I can draw the graph here in just a sec, sure. So let's take this derivative. The derivative of t cubed is 3t squared. And the derivative of negative 27t is just minus 27. And then acceleration is the derivative of the velocity, which is also the second derivative of position. Right? You can think of it in either way. The derivative of position is this, which is velocity. If you differentiate again, we use the double prime notation for that. This would be 6t, and then the 27 differentiates to 0. It's a constant. So these are our velocity and acceleration functions. If you want to graph s of t, so this is what they asked for, right? They wanted the velocity and acceleration function. I think they also wanted acceleration after 8 seconds and acceleration when velocity is 0. So the acceleration after 8 seconds is a of 8, which is 6 times 8, which is 48. And this would be measured in meters per second squared. Distance here is measured in meters. So velocity is measured in meters per second, right? How fast are you going? How many meters are you going per second? Acceleration is how fast is your velocity changing. So it's how many meters per second are you gaining or losing per second? Like every second, I'm going 1 meter per second faster. Or every second, I'm going 1 mile per hour faster. Every hour, I'm going 1 mile per hour faster, that sort of idea. So how fast is your speed changing over time? And usually you see this written as meters per second squared because you can simplify the fraction of units here into this. So this is the first thing they asked for. The second thing they asked for is to find the acceleration at the moment when the velocity is 0. So first we have to find when is the velocity 0, right? V of t is my velocity function. there are some t values for which this function is equal to 0. Those t values we would then want to plug in to the acceleration. Does that make sense? So your velocity being 0 means your position is not changing, at least at that moment. Usually this means you're changing direction, you're turning around. They want us to find what's the acceleration, how is your speed changing at that moment when you've stopped to turn around. So did you stop real hard and then turn around, or did you stop softly and turn around, that sort of thing. So first, when is the velocity 0? Well, that means v of t would be equal to 0. And I have the function for v of t, that's 3t squared minus 27 equals 0. I can factor a 3 out, and I get t squared minus 9 equals 0. And I can factor t squared minus 9 as a difference of squares. That's t minus 3 times t plus 3 equals 0. So my two possible solutions here are t equals 3 and t equals negative 3, but they've told me that t is meant to be positive here. I'm not interested in any negative t values. So t equals 3 is the one we take. And then we take this and we plug it into the acceleration. So the acceleration at that moment is a of 3, which is 6 times 3, which is 18. And again, this is in meters per second squared. So at this moment, when we turn around, when my velocity is 0, we turn around pretty aggressively. We are accelerating at 18 meters per second squared. Is this making sense? Some fun questions to ask here are like, if your acceleration and velocity are both positive, what's happening to your position? If acceleration and velocity are both positive, that means you're going in the positive direction and you're getting faster. What if your velocity is positive, but your acceleration is negative? Well, your velocity is positive, so you're going in the positive direction, but your acceleration is pulling you back. Yeah, so you're slowing down. What if your acceleration and velocity are both negative? Well, then you're going backwards and speeding up. These are all good things to be thinking about. Now there was a question about some graphing. So let's take a look at the graphs of these guys. I'm going to switch over to Desmos. Although I think the values they've given us here, these are not bad things to graph. Desmos always does a prettier job than I do. So S of t is t cubed minus 27t. Let me fiddle with these. Yeah, let me scale these down. This is y to like. Let's go something like this, right? So here's my position function. And we're told to only pay attention to what's going on to the right of 0. I don't really care what happens to the left of 0. So here's my position function. Originally, I start off at position 0, and then I'm moving in the negative direction for quite a while. And then I turn around and I'm moving in the positive direction for quite a while. My velocity function again, t greater than 0 here, looks like this. So originally, my velocity is negative, which means I'm moving in the negative direction, moving backwards. And then I turn around and my velocity becomes positive and I'm moving in the positive direction. Our acceleration function is just 6t. And again, t is positive here. So it's hard to infer a whole lot from these graphs unless you're already pretty comfortable with the concepts. But I would start by saying compare the blue and the red. Everywhere the blue is negative, the red is decreasing, right? The red decreasing means we're walking backwards. Our position is going down. We're going in the negative direction. So where the blue is negative, the red is decreasing. In other words, where my velocity is negative, my position is going backwards. Right here, where the velocity is 0, my position turns around. So I have to stop to turn around, right? If I'm walking to the left, 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 and then I want to go to the right, 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 for a brief second where I turn around, my velocity is 0. So here I am walking to the left, left, left. My velocity is negative. Walking to the left, left, left. And then I turn around and I want to start walking to the right, to the right, to the right. So that means my velocity right at that moment where I turned around had to be 0, because for that moment, in order to turn around, I had to stop for a second. And then we continue off to the right, and we keep walking to the right, and we're going faster and faster and faster. Our velocity is getting bigger, which means we're going faster and faster and faster and faster, and that corresponds to the idea of this acceleration itself being an increasing function. If we want to, we can trace what's going on here using the blue well. So I know that I'll put position 0 right here. So my dude starts out here at time t equals 0. He's at position 0. And what's he doing? Well, we know that this velocity function starts off negative. So he's going to start off walking to the left until he reaches, at some point over here, he decides, I'm going to turn around. This is at time t equals 3, when the velocity is 0. So he comes over here like this, and then he's going to turn around and start walking back the other way. The position right here, where he turned around, is s of 3, which I think we saw was like negative 54, yeah. So this would be at the position negative 54 meters. So he walked to the left 54 meters, and then he turned his happy ass around. And he continues walking to the right. And in fact, he's speeding up. He's going faster and faster and faster. They asked us to calculate the acceleration at this moment. They also asked us to calculate the acceleration at 8 seconds. So let's see, what's our velocity at 8 seconds, just out of curiosity? What is v of 8? We know that our acceleration was 48 meters per second squared, but v of 8 is 3 times 8 squared minus 27, which is 3 times, I would write it as this, 64 minus 9, so factor out the 3, 64 minus 9, that's 55, so this is 3 times 55, which is 150, plus 15 is 165, so homeboy's hauling ass over here. He's going, woo, I'm flying. This is at time t equals 8. So he started off going to the left. He's going somewhat slowly, but speeding up. And then he turns around. And briefly for a second here, you imagine if you're walking to the left and then you're going to turn around and start running the other way. For just a second there, you had to stop. You weren't going left, you weren't going right. As you were turning around, you had to stop. And then he starts running this way really, really, really fast, going faster and faster and faster and faster. So kind of that's what was going on. The position over here at t equals 8, I haven't calculated. I don't know what it would be. It'd be 8 cubed minus 27 times 8. We can ask real quick, what is that? Or I can just ask, what is s of 8? 296. So he's way out here at positive 296 meters. Just hauling ass to the right. So the interplay between position, velocity, and acceleration, they're very important, especially if you're at all interested in physics. That's really the whole game. Classical mechanics, at least. And this is that problem. Now, there was an earlier problem having to do with velocities and stuff where I asked you to do some graph sketching. I don't mind going back and taking a look at that because I think that could help us with this too, if we wanted to. Is that something we want to do? Okay. So somewhere here, right? This is the position, and we're asked to state the velocity. So let me do my best to copy this down. So this is s of t, and this is my t-axis. Chop this 1, 2, 3, 7. Okay, and we know that max here is 5. Oh shit. Do it like that. That works. All right. So from time t equals 0 to t equals 1, we go from here. So I'll bring this over so you can kind of do this. Time t equals 0 to t equals 1. We go from position 0 all the way to position 5. So we're screaming up here. Then we chill from time t equals 1 to time t equals 2. Then by the time we're at t equals 3, we're all the way back down to 1. And then we chill there for a second. And then from times 4 to 7, we are moving back out to 5. So something like this. So this is the graph of my position function, s of t. Right? And they ask us, when are we moving to the right? When are we moving to the left? When is the particle standing still? And then sketch the velocity. All right. Let's talk about this. So there's some good questions here. Kieran asks, the gaps on the velocity graph, which is the graph we're going to end up drawing, are where we're shifting directions. That's true, right? That's the idea. And then Julio's suggesting that is because he's standing still. This is not unreasonable, but let's talk very carefully about each of these pieces. I think it will be helpful for us to kind of schematic out the dude's path. So just so we're clear, this is position, this is time. So if I want to draw the dude running back and forth, his position goes from 0 up to 5. He's always running between these things. Time t equals 0, he's over here at position 0. And then he runs all the way out to position 5 by time t equals 1. So he starts by running all the way out here. And then he sits there for a second. From time t equals 1 to time t equals 2, his position stays at 5. So he doesn't move from time t equals 1 to t equals 2. But then from time t equals 2 to t equals 3, he runs back to position 1. So he comes out here, he stays for a minute, but then he does come back here. And then from time t equals 3 to t equals 4, he's just chilling there. And then from t equals 4 to t equals 7, he runs back out to 5. And that's where he stays. I don't know how to diagram him running back out, but this is sort of the path, right? He starts at 0, runs out to 5, runs back to 1, then runs back to 5. But each time he's at one of these points, he pauses for a second. So from time t equals 0 to t equals 1, my position is increasing from 0 to 5. We're running to the right. So certainly from 0 to 1, we are moving to the right. From time t equals 1 to t equals 2, we're holding still, right? We ran out to the right, and then we just sit here for a second. So we're holding still from 1 to 2. From time t equals 2 to t equals 3, we're running back to the left. Then from time t equals 3 to t equals 4, we're sitting here waiting. So we're standing still again from 3 to 4. And then from time t equals 4 to t equals 7, we're walking more slowly back out, but we're walking to the right. So this is 4 to 7. So that's my whole journey. I start at 0, I move up to 5, I sit there for a second, I move back to 1, I sit there for a second, I move back out to 5. Or I start here, I run out to here, I sit here for a second, I run back to here, I sit here for a second, I kind of walk back to here. Now sketching the velocity. If I'm holding still, what's my velocity? Zero, right? So if this is going to be the graph of v of t, sorry, this pen doesn't work as well without something underneath it. If this is going to be my graph of v of t, there are some intervals on which I know v of t must be 0. Let me chop this up. I'll call this, what do we got, 7 seconds? I need some more space here. 4, 5, 6, 7. All right, we'll do it like this. I'm still from 1 to 2 and from 3 to 4. So let's get some color up in here. From 1 to 2, I am holding still. So my velocity should be 0. Now at time t equals 1 and at time t equals 2, I'm changing my velocity. It's not necessarily 0 there. And the same is true 3 to 4, right? From 3 to 4, I was holding still. So everywhere in here, my velocity is 0. Like this. I'm actually going to need some negative velocity here too, aren't I? Yeah. All right. Let's zoom out, come back up here. From time t equals 0 to t equals 1, remember velocity is the rate of change of your position. How fast from time t equals 0 to time t equals 1 was I running over here? Well, it's the slope of this.
It's like 5.
Yeah, exactly. I go 5 meters over the time 1 second, and I'm moving in the positive direction. So my velocity here is the distance divided by the time which is 5 meters divided by 1 second, which is the slope of this line segment. So I'm just going to come up here. I'll mark this as +5. And we know that from time t equals 0 to time t equals 1, everywhere in here, I was running to the right at the constant speed of 5. Then from time t equals 1 to t equals 2, I just stood out there. So it's like, you know, someone starts the timer and I immediately start running at 5 meters per second. And then as soon as I get out there, I stop. I don't slow down or anything. It's like I just smack into a wall, right? And I stop. So I'm running, smack. And now I'm like, oh, that hurt. That really hurt. That really hurt. But now between times t equals 2 and t equals 3, we're going to do some more running. From time t equals 2 to t equals 3, I'm running back to the left. Now I cover 4 meters, right? I go from position 5 down to position 1. I cover 4 meters in 1 second. So my speed is 4 meters per second, but I'm running to the left. I'm running in the negative direction. So my velocity is -4. So I'll mark this as -4. From time t equals 2 to t equals 3, my velocity is a constant -4 meters per second. So it's like I run to the right at 5 meters per second, I smack into a wall, I fall down, it takes me a second to get moving again, and I run to the left at 4 meters per second. And I don't speed up to that, I don't slow down from that. When I get back to the time, when I get back to that position 1, I smack into another wall. I just fall on my face and I immediately stop again. And I lay there on the ground, moving at 0 meters per second for another second. And then I get up and I start walking to the right again. So I go from here to here, I smack into the wall, I sit there for a second. From there back to here, I smack into a wall, I sit here for a second. And then now, having been beat up a few times, I walk a little more slowly back out to this wall. So what is my velocity along the last leg of that journey? Well, I'm going to go from position 1 to position 5. That's a distance of 4 meters. And I'm going to do it over 1, 2, 3 seconds. So that's 4/3, right? Did I draw this graph right? Is this the graph they gave us? So what's the slope of this? That's 1, 2, 3, 4 over 1, 2. Oh, it goes out to 6, not to 7. I'm sorry. So yeah, so they gave us integers to work with. They say, forget about this. Just here. All right. So then as we go back from here to here, so we ran over here, smack, hit the wall. Ran over here, smack, hit the wall. And then walk back over here. This last walk, I'm going, I go all the, this is a bad drawing. I need to say we're going all the way up to 5. So scratch all of this. We go all the way back out to 5, but we only do it over a 2-second interval, not a 3-second interval. So then that slope is going to be this rise over this run, which is 4/2, which is 2. And we do that from time t equals 4 to time t equals 6. So the gaps that you're referring to, I think you're thinking of like these jump discontinuities, right? It's true that in real life, you don't see these. You end up with very steep things there in real life, because in real life, I can't go from 5 meters per second to 0 meters per second without slowing down. Even if I hit a wall, I'm going to slow down very fast, not instantly. But kind of think of it as hitting a wall, right? Think of it as I'm running at 5 meters per second and I smack into a wall, and that immediately puts my velocity to 0. I lay there for a second, and then I immediately start running back at 4 meters per second, and then I smack into a wall. And then I lay there for a minute, and then I get up and immediately start walking to the right at 2 meters per second. It's true that in real life, these would be steep sloped things. They would not be immediate jumps. But if we want to simplify, and this is one of the sort of simplifying assumptions that people make all the time in physics, this is not a bad approximation of something that could really happen, especially if you had like a ball, right? Especially if we're not talking about a person. If you're talking about like a ball bouncing off of walls, this could be a very realistic description. Think of how a pool ball bounces off a cushion, right? It's pretty much instantaneous. So I hope this has helped to demystify this problem a bit. I think that this is a really good concept problem. You know, to spend the time really understanding this is a great thing. Really will help you understand the physics and the connections to calculus. Are there any questions we want to ask about this? So yeah, here and here we're standing still. Our velocities were 0. Here and here we are moving to the right. Our velocities are positive. And right here we are moving to the left, where our velocity is negative. Well, the velocity, so it's not just points where the velocity is 0. The velocity is 0 over this whole interval from 1 to 2. And that means we're standing still. So right in here, everywhere in here, v of t is equal to 0. And everywhere in here, v of t is equal to 0, which means we're standing still. And then the jumps like this, the jump from v of t being up here at 5 to v of t being down there at 0 is like hitting a wall. I'm running to the right at 5 meters per second everywhere here. My speed is constant, and then smack, I hit a wall. And when I hit that wall, my velocity goes to 0. I am no longer moving, right? I am unconscious on the ground for about a second. And then my ass wakes up and goes, I should probably go back the other way. So I start running back the other way really fast. And then smack, I hit a wall and my velocity goes back to 0. And I'm like, oh, fuck, I don't understand what's going on. And I get up and I walk to the right. So each of these jumps is a very quick change in velocity. You can think of it like hitting a wall. I'm running, smack, I hit a wall. Now my velocity is 0. I get back up, I'm running, smack, I hit a wall. My velocity is 0. I get back up, I'm walking to the right. So these intervals where the velocity is 0, like everywhere in between here, these intervals, I'm standing still. I'm like lying on the ground. But the jumps here are like hitting a wall or getting up and running really fast. My velocity goes from 5 down to 0. That means I was moving and then all of a sudden I'm not moving. Or I was not moving and then all of a sudden I am moving. Right. Yes, exactly. Yep, transitions, transition points. Not necessarily meaning we're holding still, just meaning we're changing our velocity. It's a good analogy for this. So imagine you got a marble, right? And below that marble, you have like a graduated cylinder, a clear glass cylinder full of oil or water or something like that. I'm going to hold the marble way up here and I'm going to drop it, and then it's going to hit that water and it's going to slow down, right? So it's falling. It's actually going faster and faster as it falls here. But then when it hits that water, it's going to start falling more slowly. That would produce something like this in the velocity. Falling very, very fast. My velocity is high. And then all of a sudden, when it hits that water, it's going to be falling much more slowly. So a jump in the velocity function like this is a rapid acceleration, either positive or negative, meaning you go from moving fast to moving slow all of a sudden, or you go from moving slow to moving fast all of a sudden. And the only sort of place where you would see a literal immediate drop off like this is if you smack into a wall or something like that, where you have an impact that brings you from a non-zero velocity instantaneously to a zero velocity. In other words, this guy is having a really bad time right here. This guy is having a rough day right here. You've heard this old saying, it's not the fall that kills you, it's the sudden stop at the bottom. This is a very sudden stop. It's a tricky biscuit. So this is a discontinuity in the velocity function. And in real life, we don't have those. It's, piecewise, I could express this function piecewise. So the mathematics here isn't bad. It's the physical interpretation that you're going to have a hard time finding in real life. So the orange function here, I can write piecewise, f of x. I shouldn't call it f of x. I should call it v of t, because that's what it is. V of t has several different behaviors. If 0 is less than t is less than 1, then v of t is equal to the constant function 5. If 1 is less than t is less than 2, then v of t is equal to the constant function 0. If 2 is less than t is less than 3, then v of t is equal to the constant function -4. And then again, if t is between 3 and 4, we're equal to 0. And if t is between 4 and 6, we're equal to +2. So like mathematically, the gaps are just jump discontinuities. But a physical interpretation of those would be a very rapid change in velocity, which is like I'm going to use vocabulary that I shouldn't use here. It would be a pole in your acceleration, or an infinite discontinuity in your acceleration. If you think about it, you can kind of imagine this as a vertical line, right? We don't do that because those aren't functions. But if you want to, you can imagine that there is a vertical line or infinitely steep line here. And then the rate of change for the velocity, the slope of the velocity, is your acceleration. So here your acceleration is 0. You're moving at the constant velocity 5 meters per second. Here your acceleration is 0. You're moving at the constant velocity 0 meters per second. But this instant change from 5 meters per second to 0 meters per second, just instantaneously there at time t equals 1, your acceleration was -infinity. And that's what kills you, right? Because force is proportional to acceleration. So if you really did this, if you really went immediately from moving at 5 meters per second to moving at 0 meters per second, even though 5 meters per second ain't all that fast, you would actually die. You would experience infinite acceleration for that brief second, and that would crush you into a pancake.
Yes, so like what you were saying makes sense. So like I would say like an example where you would throw like a ball at a couch and the couch just instantly absorbs it, or like at snow, they would instantly just stop there.
Those are really good examples. The truth is that those examples actually look a lot more like this. They're very steep and they're rounded at the edges. So the snowball or the ball being thrown into a couch is gonna look more like this because it doesn't actually stop instantly, right? If you film that with a super slow motion camera, you will see the couch absorbing the ball and there being this little bounce reflex scenario. So in real life, you actually see shit that's much more like this than like this.
All
Um,
right, I get it.
but it's very, very close, right? And the idea is that as long as the gaps between these two things aren't too large, then this is actually not a terribly traumatic event. But for a human being, for a physical creature to actually experience instantaneous change in velocity, to have a jump discontinuity in our velocities would be lethal because the acceleration would, for that moment, be infinite. But yeah, a snowball like splatting on a wall or a tennis ball being thrown into a couch are both very good examples of this sort of thing, where your velocity goes from positive to 0 very, very quickly. It's true. Yeah, this sort of thing, certainly no human being walks like this, right? Nobody is capable of doing this. When we change direction or when we change our velocity, we do so more slowly. We do so gently, smoothly, in fact. Or at least that's the way that Newton thought of it. It turns out to be more complicated, but um, as we're building this intuition, yes, in real life, you wouldn't have a vertical sudden jump. You would have a steep slope like this. Yeah, and the same is true everywhere else here. Cool. Yeah, yeah, of course. I'm glad we have the time to do it. Is there anything else that you guys want to fiddle with here before I introduce the chain rule a little bit? It's worth saying real quick that I think the closest you'll ever get to a thing like that is what are called completely, I'm going to say this wrong, completely inelastic collisions. And the closest physical real world examples we have for that are two pool balls colliding, right? If you ever shoot pool, like when a cue ball hits another ball, the acceleration of the ball that's holding still, when it's struck by the other ball, this ball's velocity before it gets hit is 0. It's just sitting still. And as soon as the other ball hits it, it immediately begins moving off at that speed. This is the closest we get to a jump discontinuity and velocity in things that we'll encounter in real life. Totally inelastic collisions, if you want to Google it. 29 on 4. Let's take a look at that. No, don't do this. God damn it. I hate WebAssign doing this shit now. All right, 29 on 4. Okay. So we're given e to the p times the quantity p plus p root p. We have some choices as to how we want to differentiate this. I can think of this as f and this as g and apply my product rule, or I could distribute the e to the p and have e to the p times p plus e to the p times p root p, and then do two product rules. But I think the nicest way to do this, I'm going to write this, I'm not differentiating yet, just rewriting algebra-wise. This is e to the p times p plus this piece right here is p to the 1 times p to the 1/2, which is p to the 3/2. So I'll write it like this. So this means if I want to take the derivative, which would be in this case dy dp, I'm differentiating y with respect to the variable p, then I would need to, I'm applying the operator d dp to this stuff, e to the p times p plus p to the 3/2. I'll switch to the prime notation now if that's okay. So I've got one function here and another function here, and they're being multiplied. So if I want to differentiate them, their product, this is going to be e to the p primed times p plus p to the 3/2 left alone, plus e to the p left alone times p plus p to the 3/2 primed. All right, so I've got these two functions in here multiplying each other, and I want to differentiate their product. So I differentiate one, leave the other alone, and then I add that to what I get when I leave the one alone and differentiate the other. Writing things out in this schematic way, really useful, right? So I'm not even calculating the derivative yet. I'm just looking at the shape of the derivative. And then in my next step, I'll calculate the little derivative pieces. Is everybody comfy with where this line is coming from? I know this as like little f, and this as like little g. And then I follow the rule that says f times g all primed is f prime times g plus f times g prime. So here's f prime times g plus f times g prime. Good so far? All right, now let's take my little derivatives. When I prime e to the p, I get e to the p. And now I leave this piece alone, p plus p to the 3/2. Plus, this e to the p wasn't being primed, he's just chilling. And this guy I need to differentiate now. So the derivative of p, just like the derivative of x here, because I'm differentiating with respect to the variable p, this piece will differentiate to 1, plus this piece will differentiate to 3/2 p to the 3/2 minus 1. It's a power rule. Sorry, my cat is scratching the floor. No, Kitty. Where's you going, bud? You love me? You handsome. Wanna be good? Hang out with your brother. All right. So here we differentiated the e to the p. We left the other piece alone. Here we left the e to the p alone and differentiated the other piece. This guy is a power rule thing. So the p differentiates to 1, and p to the 3/2 differentiates to 3/2 times p to the 3/2 minus 1. And now we clean things up. So this is e to the p times p plus p to the 3/2 plus e to the p times 1 plus 3/2 p to the 3/2 minus 1 is 1/2. And there's really not a whole lot more you can do here that's worth doing. You can factor out an e to the p, and then you'd have p plus p to the 3/2 plus 1 plus 3/2 p to the 1/2. But I don't see a whole lot of value in that. It's really not making things nicer. So yeah, because there aren't any like terms in here I can combine. This is p, this is the square root of p cubed, this is a constant, this is the square root of p. So for my money, this is fine. Feeling good on this? Any questions on this?
Wait, so you use the chain rule or the product rule for this?
No chain rule. We don't know the chain rule yet.
Okay.
Just the product.
Oh, okay. Okay.
But that serves as a nice introduction. Let me see, actually, let me check something in your syllabus really quick. Make sure I'm not getting in order here. We need to talk about trig derivatives. Yeah, okay, that's right. Chain rule wasn't supposed to be this week. Trig derivatives are the thing we haven't done yet. Chain rule is set to be next week. So let me go ahead and introduce trig derivatives now. They're not in your homework this week, and they will be in your homework next week. That's where we're going to start. If I wanted to cook up the derivative of sine, f of x is sine x, then f primed of x would be the limit as h goes to 0 of the sine of x plus h minus the sine of x all over h. And this is not an easy limit. It's really not. For a bunch of reasons. I mean, the obvious one is if you plug in 0 for h, the top and bottom are both 0. That's true for all of our derivative limits. But the sine function makes this hard to work with because it's not like the algebra of the sine function is simple, right? Sine of x plus h is not the sine of x plus the sine of h. It's much, much worse. It's the sine of x times the cos of h plus the cos of x times the sine of h. And then over here, we still have minus sine x. So the formula I'm using is the sine of a plus b formula. This is sine a cos b plus cos a sine b. And I'm just using, x as a and b as h. H is b. All of this is still being divided by h. And if I want to get something out of this, then kind of think about the proof of the product rule where we grouped some terms. So I'll call this group 1, I'll call this group 2, I'll call this group 3. I'm going to put 1 and 3 together. So I get lim h to 0 sine x cos h minus sine x all over h plus cos x sine h all over h. From the first group there, now from that first piece, I'm going to split the limit up. So I'll have lim h to 0 sine x. I can factor cos h minus 1 here, so I'll have like this, plus, and then lim h to 0. I won't do anything here. I'll just leave this as cos x times sine h over h. So just a little bit of algebra and limit laws. From this first bunch here, I can factor out the sine x. And what's left is cos h minus 1. And it's all still over h. And I give the limit separately to this piece, where I don't do anything. But the neat observation is that you can this guy out here, and you can yeet this guy out here. So you get sine x times the limit as h goes to 0 of cos h minus 1 over h plus cos x times the limit as h goes to 0 sine h over h. And these two limits are both wicked hot, right? This is tough. This is tough. So it turns out the first one of these is going to be 0, and the second one of these is going to be 1. But it's going to take a meaningful amount of work to show both of those. So what we're going to end up with out of this is that the derivative of sine is sine x times 0 plus cos x times 1. In other words, the derivative of sine x is cos x. But the details in these limits are genuinely challenging. Now, the good news is, once you do this for sine, the limits, the special trig limits that you need, these guys are the same special trig limits that you need to get the derivative of cosine out. So let me try to convince you that this limit is 1 and that this limit is 0. I'm going to use Desmos. There's nothing wrong with looking at some graphs. Whoa! All right, let's rescale these axes. Y is going to run from -1 to 1. There we go. There we go. So here's sine h over h. Notice that as we get closer and closer to 0, this y value really is getting closer and closer to 1. In fact, it looks like 0, 1 is on the graph. but is not. There's a hole here at 0. That's why it's fighting me. It doesn't want to show it. All right, there it is. There it is. Undefined at 0. All right, so this is really what the graph of this thing looks like, but the limit is 1. Now, this graph should convince you that that limit is 1 if you trust that this graph is correct, and hopefully you do, because Desmos is not out of its mind. It's just a computer. But to prove to you that this limit is 1, I'm going to need to do some pretty clever geometry. So that is something I will save for next week. And then once we have that this limit is 1, I'm going to do some algebra and trig manipulations to use that limit to show that this limit is 0. The upshot is the derivative of sine is cosine. And it's very easy to show using the same sort of calculations once we have those limits that the derivative of cosine is sine. d dx of sine x is cos x, and d dx of cos x, it's not exactly sine of x, it's negative sine of x. Because the formula for cosine, cos of a plus b, has a minus sign built into it. Otherwise, it looks very similar to this shit, but you'll end up with a negative. Good practice with the product and quotient rules. We should tuck these away, right? These are obviously hugely important. Sine and cosine may be the two most important functions in all of mathematics. E to the x has a good running chance up there. Turns out they're intimately related to each other. Good practice with the product and quotient rules to get the derivative of secant, tangent, cosecant, and cotangent from them. So I'll leave you here, and then we'll fiddle more with this next week. Practice. Let's find d dx of secant x, d dx of tangent x, d dx of cosecant x, and d dx of cotangent x using product and quotient rules. So I'll do the first one here for you. d dx of secant x, well, you got to remember what secant x is. Secant is 1 over cosine. So you can apply your quotient rule. High d low minus low d high over low low, right?
Yeah,
So this
it's
is,
low D high, but
oh shit, yeah, I always get those swapped around. Low d high, yeah, you're right. So this will be cos x times, yeah, the derivative of the top minus the top times the derivative of the bottom over the square of the bottom. It does matter. If you get those backwards, then the result will come out wrong. It'll come out negative. So here we'll have cosine times the derivative of 1. So that's cos x times 0 minus 1 times the derivative of cosine. That's negative sine of x. And then all of this is being divided by cos squared of x. Well, cos x times 0, that's 0. And negative 1 times negative sine is positive sine. So I get sine x over cos squared of x. And the nicest way to spot this, or to remember this, is to write it as 1 over cos x times sine x over cos, because that is secant x times tangent. So the derivative of secant is secant tangent. Similarly, we can calculate the derivative of tangent. It will come out to secant squared. The derivative of cosecant will come out to negative cosecant cotangent. And the derivative of cotangent will come out to negative cosecant squared. But you guys should take the time and do those calculations on your own. And next week, we will grind a little bit more with trig derivatives and the chain rule. And that's going to be a lot of fun. So like I said earlier, I don't want to get you too far ahead of my other class, my other Calc 1 class. I do want to keep you guys on similar pacing. So I will go ahead and end our lecture here for today. Are there any burning questions before we end the session? Yeah, sure. Alrighty then, I'll go ahead and end it here for today. We got about 7 minutes left, so if you do have homework questions or anything you want to ask about, you can hang around and we can talk about those.
Professor,
The lecture. Yeah.
hello. Yeah,
Hey.
someone put something in the chat.
Yeah, I see it. So Katie's going to hang around to ask some homework questions. Karen wants to talk about the exam. So the exam 1 is going to be after we finish the chain rule. And the way I like to do this, after I finish the lecture, the last lecture that's on that exam, I give you a week before the test. So I think probably next Wednesday, we will finish the lecture on the chain rule. So exam 1 will probably be Wednesday after next. So next Wednesday, or whenever we finish the lecture on the chain rule next week, I will release the study guide. And then you guys will have a full week to work on the study guide before the exam itself. So if you're wanting to mark days on the calendar, right now it looks most likely that exam 1 will be not next Wednesday, but the Wednesday after that. And the date there is not the 3rd, but the 10th. So I would count on having your exam around the 10th. Yes, so here's the business with the proctoring. We all have these webcams, right, on our laptops or whatever. So you're going to use HonorLock like normal. And if you don't have a laptop with a good working webcam, let me know. We have a laptop loan program at Santa Fe. I can get you one for free, no cost, no nothing. And then the other thing you're going to need to do is sign into Zoom on your phones. And you're going to like balance your phone up against a coffee cup or something so I can see your writing surface. I need to see your papers, your hands, your whole desk. On Zoom. So we will talk through that and work through it on the day of the test when we're getting things set up. You know, I'll take time to talk to everybody and make sure everything is okay. If you have issues getting any of that tech, either you don't have a working webcam for your laptop or you don't have a phone that you can run Zoom on, let me know. I got lots of extra old phones I can loan you, and the college has laptop loans that we can give out. So go ahead and install Zoom on your phones. And you might want to practice signing in there, make sure you can get signed in and stuff. But yeah, that's going to be the proctoring system. Ben asks, is it possible to do the exam sooner than Wednesday the 10th? It's going to depend on the pace at which we go through the material, but I think that's probably about as soon as we could hope to do it. So we will not likely finish the material before Wednesday, the 3rd. And then I really do want you guys to have a week to spend with that study guide and ask questions and share your work with me and get some feedback before the test. If there's something crazy going on, if you got to go out of town or you're expecting some sort of schedule conflict, that's a different thing. I can schedule the exam, like a makeup exam for you at a different day if necessary. Other questions? All right, I think I probably do have time for one problem here, Katie. What was the homework problem you wanted to see?
So when we did number 29, I was doing it with you and then I plugged it into the website and it said it was incorrect.
Let's see. So that was this guy, right? E to the P times P plus root P, P root P?
Yes.
Let's see. Here, right? So p times root p is p to the 1 times p to the 1/2. That's p to the 3/2. And then 3/2 minus 1 certainly is 1/2. So I would check and make sure you've got it exactly as I have it here. Or maybe just run through the calculation fresh, because this is correct. E to the p times this plus e to the p times this primed. This is definitely going to be this plus.
Should we put it as the second line or the last line?
Doesn't matter. Doesn't matter. I think this is probably the most natural way to write it, given the steps above. But both are correct.
Oh, I just realized I used X instead of P. Sorry.
Yeah, no, it's okay. Was that the only thing you wanted to look at?
Yes.
Okay. All right, then I will go ahead and conclude our lecture here. I do have my normal office hour today from 1 to 2 if you guys want to come by and work more homework problems. Otherwise, I'll see y'all on Monday when we'll talk more about trig derivatives and the chain rule. Take care, guys.